So thank you for this introduction, and thank you to the host committee for this opportunity to present my work today. So my name is Jordan Cossu. I'm a second-year PhD student working on the project Selection and Characterization of DNA Aptamers against the CD20 antigen. This project is a collaboration between two labs, both located in Grenoble in France, so the DPM and the DCM. I would like to start this presentation by a short introduction of the context behind this project. So since a few decades, the biotechnological progress enabled the development of new pharmaceuticals, more and more sophisticated, such as the monoclonal antibodies, which can recognize and bind to one specific target. Their use as complementary treatment, for example, in the cancer therapy, led to a slight decrease of the adverse effect that we had. However, despite these well-known benefits, their use in routine still suffer from a few limitations, such as their immunogenicity, their expensive production, which requires the use of animal cells, so which bring ethical question, and their low tissue penetration, for example. So the aim of this project is to design multivalent monoclonal antibody mimics in a synthetic way, which would be smaller, cheaper, less immunogenic, but still specific for their target. So the model that we choose to do that is the Rituximab, which is the first monoclonal antibody that has been commercialized as a therapy in the end of the 90s, and which is used to treat the lymphomas, so blood cancers. This antibody recognizes the CD20 antigen, which is a transmembrane protein overexpressed on two mature B cells. And this couple has been studied a lot, which gave us information which allowed us to identify two regions, each represented in green and purple, or maybe was it magenta today, which are mainly involved into the interaction. So for this project, we decided to use this 25 amino acid peptide as a target, as we also have a project of a synthesis of mimics using peptide issued from the FA of the antibody. So the very first step of this project, and then I mean, to synthesize two peptides. So the first one here, issued from the native sequence of the CD20, and the second one here, which is a scrambled version of this peptide, meaning that we shuffle all the amino acids except for the cysteine here and here, in order to get the best negative control. So we kept this position for both cysteine as they are involved into the formation of the cysteine bridge, and we wanted to get the whole structure for both our control and our target. Yeah, so still not working. Yeah, now I will give you a bit more details about the method that we choose and the conditions. So I don't think that I need to define aptamers to you, but it's important to just say that aptamers are low immunogenic and low toxic in vivo. They are easy to synthesize and to modify, so they are cheaper than monoclonal antibody. Their storage conditions are also way better. And mostly they are fully synthetic, so they can overcome most of the limit I presented in the beginning of this talk. For this project, we started from a library containing 77 nucleotides. So you can see here both priming region, and in the middle, 30 nucleotides that were just random, leading to a theoretical number of about 10 to the 18 sequences. But as Dr. Gregory Penner said yesterday, this number is just theoretically. In fact, we had more, around 10 to the 10 different sequences. So we performed this selection by a combination of the selects and a separative method called the capillary extraphoresis. So here is how it works. The first step is the incubation of the targets and the DNA pool. So in this case, the CD20. And then we inject this into the capillary. So it's just a few nanoliter. We then applied an electric field onto the capillary, which will lead to the creation of an electroosmotic flow and to the migration of the compound depending on their electrophoretic mobility and their structure. So what we expect to see here is a good separation between each our species. So first, the DNA pool. So it's important to know that all the sequences will migrate with the same velocity. It does not depend on their structure. The peptide and of the complex formed between these two species. And that's the part we are interested in the very first place. So we want to collect the DNA bound to the target, then to amplify it using PCR to start again the cycle a few more times to improve our selections. In the end of this process, the DNA pool is sent to the sequencing. So to do this selects, we started from this buffer called the TGK buffer, which has been used in the lab for a previous selection of a peptide very close to this one, just a bit bigger. And we try to optimize the condition by changing the pH, but also by changing the binding buffer. So for the incubation, by adding magnesium. And in the end, those are the conditions that we found to be the best with an incubation time of 40 minutes. So we did a 4-cycle selection, changing for each round the ratio between the target concentration and the DNA concentration by a factor of 10 in order to improve our selectivity. And here is an estimation of the KD, of the dissociation constant we had for each cycle. So I didn't put the cycle called 0 before collection, as we couldn't estimate anything. And what we can see here is that we have a slight improvement of the selectivity. Here is what we had in the very beginning. So here is the free fraction of DNA, so the unbound fraction of DNA. All of this is obtained through a fluorescent detector, as our library is labeled with fluorescein. So here is the unbound DNA. Here is just an internal reference that we use to compare the different conditions in the beginning. And here is the complex that is formed between these two. So a really small complex in the beginning. But still, we decided to collect this time area in order to do the amplification and see what we could have in the end. And here is what we had after the 4th cycle of selection. So here in blue, you have the free DNA after the first round, so the reference. And we added the peptide for the red curve. So what we can see here is a slight decrease of the height of the plateau, also a change of the shape of the peak, and here a formation of a complex corresponding to our collection windows. At this point, we decided to do the same with the scramble versions of our negative control to see if it was necessary to do a counter selection. But we observe almost no changes here and just a very small complex here. So we decided that maybe it was not necessary to do a counter selection at this point. So we sent our DNA pool to the sequencing, which was performed by a company called Biofidel in Lyon, in France. And here is what we get. So more than 160 different sequences. And here are the number of copies for each of these sequences. So as you can see, and as some said yesterday, we had no more than 1 copy for most of our DNA pool. But for 5 aptamers, we had 3 copies. So we just started working on these 5 aptamers, expecting to see good specificity and a quite good affinity for the target. So we started by doing an alignment of these 5 sequences in order to see if we could isolate a motif that would be common to all of the sequences, or if we could have a different aptamer that might be recognizing different part of the target, which could be interested for the formation of the multivalent compound in the end. And in fact, we didn't really have a motif common to all of the sequences. So we started the characterization. First, I will focus more on aptamer 1 and aptamer 2, which gave us the best results, but I will still present the result for 5 aptamers. So here are just proposed a secondary structure obtained through the software Enfold. And we started using the capillary extraphoresis in the exact same condition as for the selection in order to see if we could find this decrease of the free fraction again. And here is what we observed. So in the left, you have aptamer 1 and aptamer 2 with addition of the target compared to the reference. So we clearly see kinetics and a decrease of the free fraction of DNA. And same for this one, even if it's a bit less strong, we have a difference of the shape of the profile. When for the scramble, this time after additional scramble, we saw almost no differences. So here is a resume of the result we had. In fact, we had 3 aptamers that interacted with the target, but one of them, the number 4, also interacted with the scramble version. So we decided to just keep aptamer 1 and 2 to do the further analysis using ITC. So the KD that we estimated were around 100 micromolar, which is, I guess, pretty high for all of you. But as it's just a monovalent compound that are not optimized and that might be grafted onto multivalent compound, we decided to continue as the specificity is really important. So we did first ITC using the exact same condition, which may not be the best condition to see the interaction, but we wanted to compare the result that we had in the capillary extraphoresis. So we started by just injecting the peptide into the buffer to have a negative control. And then we did the same with the aptamer, which allowed us to do a one-to-one binding model fit. And we did that for all 2 aptamer and targets. And we saw kind of the same result as we had using the CE with KD around 100 micromolar or 140 micromolar for both aptamer 1 and 2. When for the scramble, we had mostly non-specific interaction and we couldn't even fit for aptamer number 2. So here is a comparison and a resume of both the result that we have. So what we can conclude here is that capillary electrophoresis was a good method to first assess the specificity of our compound for our target, but also to estimate the KD, even though these were just a bit lower than one we obtained using the ITC. And finally, we have compound with a medium affinity, but a really good specificity for our target. And here we can see with the M value that the model we used to do this fit was pretty good, pretty accurate. So to conclude this presentation, here are the steps I presented today. So we are at the very beginning of this project. It was just the first year of my project. The next step would be first to try to do truncation in order to smaller the size of our aptamers and maybe improve the constant. Then the best candidates might be grafted onto cyclopeptidic scaffold, which look like this. So we call this compound graft, which are cyclodecapeptide containing lysine that we can add 4, 5, 6 lysine in the middle, which can be functionalized easily in order to do click chemistry, so oxime formation, as a true alkyne click chemistry, in order to graft different compounds such as the aptamers on this side of the product, or maybe fluorescent molecular or cytotoxic agent on the second phase of our compound. And maybe later on, we could try to do in vitro and in vivo tests with these multivalent compounds. So I would like to thank all the persons that work on the project, and I would like to thank you for your attention. And if you have any question, I will be glad to answer to you.